Hello, this is Professor Keen and welcome back to Electricity, Magnetism, and Light. We've been looking at Newton's optics. Specifically, we've been focusing on his definitions and his axioms. In the last lecture, we talked specifically about his axiom number 2, which came to be known as the law of reflection. That is, when light bounces off of a reflecting surface, it says something about the angles of incidence and the angle of reflection. We also focused on axiom number 5, which came to be known as the law of refraction, or sometimes Snell's law, which makes a claim about when a ray of light goes from one medium into another, there's a relationship between the angle of incidence and the angle of refraction. That was explained in figure 12.1 on page 142, where, just to remind you, in that figure, if a light ray is traveling along from A to C, and it strikes the surface of water, which is represented in this diagram by RS, then after having done so, it bends. That is, it follows a new path. It goes from A to C and then down to point E, so it bends toward the normal. And the specific amount of bending depends on the type of material from which it comes and into which it goes. So in that last lecture, we explained how Newton used this diagram to explain his law of refraction. The next thing that Newton does is he goes on to talk about the use of this law of refraction in other more potentially complicated scenarios. So he explains in figure 12.2 on page 142 how the light bends when going through a prism. He says at the bottom of the page, "In like manner, if there be a prism of glass, that is, a glass bounded with two equal and parallel triangular ends, and three plain and well-polished sides, which meet in three parallel lines running from the three angles of one end to the three angles of the other end. And if the refraction of the light in passing across this prism be desired, let ACB," and now he refers to figure 12.2, "let ACB represent a plane cutting this prism transversely to its three parallel lines or edges there where the light passeth through it. And let DE be the ray," and here I'm going to show, I've zoomed up on this diagram. So I show it right here. He says, "Let DE be the ray incident upon the first side of prism AC, where the light goes into the glass. And by putting the proportion of the sign of incidence to the sign of refraction as 17:11, which is the appropriate ratio in going from air into glass. So if you make this ratio 17:11, we can find EF, that is the refracted ray. Then, taking this ray for the incident ray upon the second side of the glass, BC, where the light goes out, we can find the next refracted ray, FG, by putting the proportion of the sign of incidence to the sign of refraction now as 11:17. For if the sign of incidence out of air into glass be to the sign of refraction as 17:11, then the sign of incidence out of glass and into air must on the contrary be to the sign of refraction as 11:17 by the third axiom. So he's referring here to the fact that if you go from air to glass and follow the refraction of the ray, if you go from glass to air, it will follow the same kind of bending trajectory. That's what he's depicting in this figure. So in this figure, just to point out, what is this dotted line that then continues from F to D? You might imagine if you have a candle located at point D, and the light coming from the candle, of course, it's going in all different directions. It's coming out from that candle, but he's tracing a particular ray of light that goes from D to E, bends through the prism from E to F, and then goes from F to G so that you see it with your eye located at that position. Now, where do you perceive this candle to be located? Well, you perceive it to be located at point little d up in the left-hand corner. Why is that? Because you perceive things to be at a location that you extrapolate the ray of light arriving at your eye to have come from. So the line GF little d, if you continue it on there, that is where you would see the candle to be, even though the light actually came from capital D to E to F to your eye. This is important. This is an important thing to keep in mind when perceiving images of objects. Okay, Now, the next thing that he does is he talks about how the light rays from an object bend when going through a lens. He has in mind understanding how, for example, a telescope or a microscope would work. So, now in figure 12.3, on the left-hand side, he depicts an object. It's an arrow, vertical arrow, PQR. And then he shows, of course, there's light. If you have, this is an ambient light. You might think about it being illuminated under some overhead lights. So the light is reflecting off this object, capital PQR. And each of those light rays could be traced, the light reflecting off every single point in all these different directions. But he is selecting particular rays of light to be illustrative or to illustrate the way that the light is going to move from a particular point, such as P. He's looking at 4 or 5 different rays coming from capital P. As they go through the lens, they bend at each of the surfaces, and then they're focused at a point little p. And likewise, if you think of a point big Q on this object where the light is bouncing off, you can trace an infinite number of rays. He's looking at 4 or 5 of them. He's showing how they travel through the lens that's located in the middle of the diagram, how they bend at each of the surfaces, and then how they focus at little q. And likewise, the point capital R on the object, he's tracing 4 or 5 rays of light as they go through the lens and focus at point little r. So I'll just read what he says here. He says, much after the same manner, if ACBD in figure 12.3 represents a glass spherically convex on both sides, usually called a lens, such as is a burning glass or a spectacle glass or an object glass of a telescope, think a magnifying glass, and if it be required to know how light falling upon it from any lucid point capital Q shall be refracted, let capital Q capital M represent a ray falling upon any point M of its first spherical surface ACB. And by erecting a perpendicular to the glass at the point M, find the first refracted ray capital M capital N by the portion of the sign 17 to 11. So he's reminding us, how do we find how this ray bends? That was going from Q to capital M. Well, you erect a perpendicular to the surface. You find the angle, the sign of the angle of incidence, the sign of the angle of refraction by using the ratio 17 to 11. Let that ray in going out of the glass be incident upon capital N, and then find the second refracted ray, capital N little q, by the proportion of the signs 11 to 17. And after the same manner may the refraction be found when the lens is convex on one side and plane or concave on the other, or concave on both sides. So he's providing us with a strategy for tracing the path of rays of light going through surfaces of either convex lenses or concave lenses or planar lenses and so on. Interesting to note is that if you were to place a sheet of paper, let's say, over at where little p, little q, little r is, if you were to place a sheet of paper there, you would form an image of the original object, capital P, capital Q, capital R. You would form an image at that location.